All right, everyone, I'm back here with some new alien technology for you guys. We're going to talk today about multiplexing. So for a multiplexer, it's essentially a combinational logic circuit that selects one input, that says output, but that should be input, to be delivered basically to the output. So essentially if we have maybe 2 to 4 to 8 inputs, and we actually just want to see one of those input for data collection, a multiplexer allows us to actually design and then actually appropriately gather that specific input. Now, how does this work? Now, this is actually one of the first times in this class that we're truly designing something strictly off a need and then actually going through a process in order to actually derive the combinational logic that's going to help us actually go through and then perform the operation that is specifically a requirement to select one input to actually be parsed to the output. Now, don't get confused though that if you've seen the fifth element, this is different than the multipass. We're not talking about multipasses, we're talking about multiplexers. So another way of actually calling a multiplexer by a different name is just basically a mux. So anytime you hear mux, they're talking about multiplexing. So let's take a look here. We're going to look first at a 2-to-1 multiplexer, and we're actually going to design that. Now, for a schematic diagram, usually it looks something like this, where you have an input and then your second input, your selector bit that actually goes through, and based off that selector bit, it will parse out the appropriate input to that output. So at any given point, we can actually, by changing that selector bit, either grab I0 or I1 as basically being our output. So how do we actually start off with the design? Well, number one, we start off with actually the selector bit itself and trying to determine how many selector bits we actually need in order to design this system here. So the number of selector bits that we actually work with are generally going to be from the form of 2 to the n, which actually equals the number of inputs. So in this case, we have 2 inputs that we're going to look at actually selecting. So if we look at 2 to the n is actually equal to 1, and that would actually be the number of selector bit that we would actually have in order to satisfy the fact that 2 to the first is equal to 2, which is actually our number of inputs. So essentially, for this system, we start off with having a requirement of 3 individual inputs. So let's design a truth table, and with that truth table, as we have seen in the past, we can take that truth table, we can actually put it into a K-map, then therefore we can actually provide an optimized Boolean expression that we can derive combinational logic from. So let's take a look. All right, so 3 inputs, so that means we're going to have 2 to the third possibilities or 8 possibilities of each different combination for which we could actually have an output. Now, if we look here, we have the selector bit. So our first bit, that's just basically going to be a 0 or a 1 for basically selecting I0 or I1. And then we have the possible combinations of I0 as well as I1 too. So here's 0, 0, 0, 0, 0, 1, all the way down to 1, 1, 1, which just represents the combinations that we could possibly have for utilizing not only the selector bit, but also I0 and I1. Now, for here, and this is actually a little bit different than what we've done in the past, we're actually going to write out exactly what we want the output to be. And so for here at that output, we're going to say with selector bit being low, or 0, 0, 0, 0, we just want to actually grab whatever I0 is. And so if we look here, I0 going down the truth table, we have 0, 0, 1, and 1. That means that whatever I0 is, I want that to be the effective output. So sure enough, here we get 0, 0, 1, and 1, which is exactly whatever I0 is going to be. Well, when the selector bit goes high, or basically the second option that we have for basically how the selector bit can either be 0 or 1. When it goes high, we want for the output to be whatever I1 actually is. So if we go down, we see that I1 as the selector bit is high within the truth table is actually 0, 1, 0, 1. So from here, we can actually make the output to be of that same form, 0, 1, 0, 1. So if we look at the truth table, half of the truth table is actually going to render an output of basically being I naught, and then the other half of the truth table is going to render whatever I1 actually was. So all we have to do in order to optimize this so that we actually get a good function that we could actually go through and derive combinational logic from as we've done in the past, let's put this into a Carnot map and see if we can do any grouping of those ones so that we can actually get an optimized output or optimized Boolean expression for that output. So let's take a look here at the Carnot map. So we basically have ones in these portions of the table, 1 and 1, 1 and 1. So obviously there could be multiple ways that we could actually do the grouping, but the most efficient and optimized way for the grouping would actually to be to group the ones at the top, then group the ones at the bottom. And once we do that at the top, we actually get rid of, in this case, I1, in which we would have I naught and S bar. And then down here, we actually get rid of I naught and leave I1, and then ended with basically S, or S being high, essentially. So the optimized output for the 2-to-1 multiplexer, and that Boolean expression for the output is in fact actually S bar ANDed with I naught, and then ORed with S by itself, just ANDed with I1. And this is a very, very, very simple expression that we can derive some form of schematic for. And sure enough, we have basically 2 AND gates and 1 OR gate, which is sure enough what we have here. 1 AND gate, second AND gate, and then our OR. And then we also have basically an inverter in which we actually use to gain the value of S bar. Now the nice thing here with this is that we essentially have derived the schematic for a 2-to-1 multiplexer, and there's actually two very specific parts of that multiplexer within the schematic. And the first is what we call a decoder. The second is the enabling circuit. So the decoder actually takes whatever values of S, or the selector bits, and then actually appropriately turns those into either S by itself or basically the inverse of that bit. So the decoder basically just takes S and gives us two different separate inputs for each AND gate here. That has its own value for I naught as well as I1. The enabling circuit here is what actually causes essentially I naught or I1, or what we're going to see in just a bit, whatever inputs that we have to actually be put to the output. Now, how does this actually work? Does it actually work? Let's take a look. Well, when S is actually low, so that means if we have S is equal to 0, S bar actually causes this to actually go high. So let's investigate this. So if S is equal to 0, maybe you guys can't read that. So if S is equal to 0, then that means that S bar comes to 1, in which we AND that with I naught, and then ORed with 0 ANDed with I1. What this means, guys, is that if S is actually equal to 0, it doesn't matter what I1 actually is. If I1 goes high, the output's 0 for this section. If I1 is low, it doesn't matter. This portion is always ANDed to 0, so it doesn't matter. However, if I naught goes high, then 1 ANDed with 1 will be the output of I naught. Or if 1 is ANDed with 0, then the output's actually 0. So in this case, we would actually see that the output would be whatever I naught is. And that's the actual true function of the multiplexer, is that we actually have here basically the output being whatever the input of I naught actually is. Let's switch this up. Does this work, in fact, actually for I1? So I wanted I1. Let's say that S goes high, which should effectively select that value, or basically that input of I1. So sure enough, if S is equal to 1, then S bar goes to 0. And here we actually get S as being 1. So conversely, as we saw with I naught, if S is 1, then whatever the output of I1 is, if it's 1, then the output goes high. If I1 is 0, then the output goes to 0. It doesn't matter whatever I naught is, because that input is always being ANDed with 0. So this right here is always equal to 0, and this portion is always going to be ORed with I1. So that's basically how a 2-to-1 multiplexer works. And here's the kind of takeaway with the 2-to-1 multiplexer, is that the process for designing a 2-to-1 multiplexer is the exact same as the process of designing a 4-to-1 multiplexer, an 8-to-1 multiplexer, or even basically a 16-to-1 multiplexer. It's the exact same process. We basically write out our truth table, we get an optimized function, in which the optimized function is always going to be of this form. And then we can actually basically design a decoding circuit and then an enabling circuit. 4-to-1 multiplexer, which is what we're going to look at right now, is just a little bit different in terms of the schematic design, but essentially the exact same function. We're just going to draw it a little bit differently. Here we actually have S, and we've parsed that out with basically an inverter. But what happens when we have multiple inverters that we're going to actually have to use, and multiple variations of the input? Well, going back to Ms. Perry's question about buses, we're going to utilize basically bus bars in order to gain basically and pull off whatever value of S1 or S bar or S naught or S naught bar we actually wanted. So let's move the camera over just to the right. Oop. All right, guys. So 4-to-1 multiplexer. So that means 2 to the n is equal to 4 inputs. Therefore, n has to be equal to 2 selector bits, because 2 to the second power, that's equal to 4 inputs. Now, that means if we have 4 inputs and 2 selector bits, that means that we actually technically have 6 inputs. And I don't want to write out essentially 2 to the 6, basically different lines within the truth table. That's a huge truth table. The thing is that we can actually write out a shortened or simplified variation of that truth table simply by looking at the selector bits themselves. Now, we saw before in the 2-to-1 mux, if S was low, then the output was actually going to be I naught. If S was high, then I1 would actually be selected. In this case, let's just look at S1 and S0, and that's the only thing that we're going to concern ourselves with, because here I'm going to say that when S1 is low and S0 are both low, then I want the output basically to be whatever the input of I naught is. When S1 is low and S naught is high, then I want I1. When S1 is high and S naught is low, I want I2. When S1 is high and S0 is high, I want I3. And from here, guys, we can easily just go through and derive this Boolean expression here for basically that output is actually being S1 bar, S naught bar times I1, ORed with ORed with S1 bar, S naught, and then I1, and ORed with S1, and then ANDed with S naught bar, and then I2, and then ORed with S1, ANDed with S naught, and then I3. So from here, guys, we can take this Boolean expression and once again rederive a combinational logic circuit that's actually going to essentially perform this exact function here. So here I'm going to basically take 4 bus bars of the form of S1, S1 bar, S naught, and then S0 bar. And so if we basically pull these down, then we can actually just essentially do what we call quote-unquote tie off to whichever one that we want. And we know that we're actually tying off to it by actually putting a dot within our schematic. So as one of these inputs goes all the way across, we know that even though it's crossing and intersecting with basically all these other inputs, the dot is where the true connection actually happens. So if we look here, first part was S1 bar, and it with S0 bar, and then and it with I0. Sure enough, we have an AND gate here with I0. We basically pull off S0 bar, which is basically S0 inverted. And same thing with S1 bar. It's essentially S1 inverted. So we can pull off S0 bar, S1 bar, and then I1, that's actually going to be ANDed, in this case, with S1 bar as well as S0. And sure enough, here with I2, we get S1, and then S0 bar, and then I3, we get S1, and then S0. And then we basically OR all the outputs from each of the 4 AND gates together, and therefore we get an output. Now, what I generally have students do is go through and design either an 8-to-1 multiplexer or a 16-to-1 multiplexer. Those designs are no more difficult than what we just did. It's just a little bit more work. The trick is that if we have 8 inputs, then we should have basically 3 selector bits, because 2 to the third is equal to 8. Therefore, we just have 3 selector bits. So essentially here we would have, instead of having four bus bars, we would actually have 8 with three of those actually having inverters on them. And in this case, all we would have to do is just basically provide 4 additional AND gates, or 8 AND gates going all the way to our OR gate. So what I'm going to be having you guys do is design those on your own, whether it's 8-to-1 or 16-to-1, and we will talk about it on Microsoft Teams. I'll see you guys later.